Fluids flow through porous media along the interconnected pores, defining the geoplumbing of the material. Today, we're going to look at permeability data in order to corroborate some of the theoretical models, but now, being physics inspired, we would like to remain data driven. So we're actually going to look at lots of real data. And we're also trying to identify some bounds to limit possible range of material parameters. Before we go any further, let me remind you that there are two key equations that we're going to use in the fluid flow. The first one is Laplace's equation that tells us how the total energy varies at any given point in the x and z direction, or x, y, and z. And we know that that is the Laplacian. But what I would like to highlight is that the Laplacian is not a function of permeability by the time we get to this part of the equation after many assumptions. But even if we had assumed that the permeability was different in x and in y, so it would kx would appear on the left element and the kz would appear on the second one, still you can multiply both sides by 1 over kz, and you would have kx over kz multiplying the second of h with respect to x twice, and there will be 1 multiplying the second of h with respect to z twice, meaning that what remains is the anisotropy ratio, which does a distortion of the geometry, but doesn't have such a major effect. On the contrary, if we take Darcy's law, which tells us that the flow rate is proportional to the permeability, the gradient of the total energy, and the amplitude, the total energy here, once again, defined in terms of the total head, we realize that the flow rate is directly proportional to the permeability. And this is the real challenge, because permeability varies in 10 orders of magnitude or more, much, much more than the difference between the richest and the poorest person in our countries. And so this is really mind-boggling, that a parameter that will define the number of pumps that we need, for example, to drain an excavation, to keep an excavation dry, is linearly dependent on a parameter that varies in orders and orders of magnitude. So that is the reason why today we are going to emphasize the issue of hydraulic conductivity in order to understand what it actually means and what affects it. So we started in the previous presentation trying to understand the physical foundation of permeability. We realized that it was very similar to a parachute. In other words, it's the balance between the drag force and the driving force, which in this case is the pressure difference along a tube. And we represented the soil as a series of parallel tubes in order to obtain the Kozeny-Carman equation. And let me remind you that in the Kozeny-Carman equation, the first few components are all material parameters, viscosity and the mass densities of water and the mineral and gravity. However, here was the permeability being inversely proportional to the specific surface to the second power. And then some function of porosity or void ratio, but as you will see, it has a relevant but secondary effect compared to the importance of specific surface. So now let's take a look at real data. This is a compilation of data for 92 different soils. And at the top, where the permeability is high, that is where the sands are, clean sands and gravels. At the bottom, and now dropping by almost 10, 12 orders of magnitude, here are the clays. Probably this is a bentonite, red here at the bottom. The data is plotted in log-log scale. And it really linearizes in log-log scale when you look at the wide range of data sets. Therefore, we would like to understand what are the parameters that control this. And if you have an intuition that permeability is controlled by porosity, you really have to reassess that intuition, because look, the soils with higher porosity are the clays, yet they are the ones with the lowest permeability. So it's not following the line that higher porosity, higher permeability, and there must be something very important and fundamental behind it. So let's take a look at this data now and try to come up with an estimate of the pore size, because that is where the fluid is flowing through. And we're going to make a very simple estimate of the pore size, and you can use different models. You could use spherical particles, but let's take a look here at platy particles, like in a clay, a dispersed clay. The plate thickness is H, and the pore size is dP. Now, the void ratio is dP over H. The specific surface, as you may remember, is twice 2 areas divided the volume times the mass density, so you get area meter squares per gram. And now I can replace the H in the void ratio and pull out the mean pore size as a function of void ratio and a specific surface. And look what happens. The hydraulic conductivity now collapses onto a single line as a function of this estimate, this rough estimate of pore size. So let me go back. This was the data. By the time we, instead of using void ratio, we correct the void ratio for pores, for a specific surface to determine an assessment of pore size, all the data collapses onto a single line. That is highlighting the importance of pore size, but also the importance of specific surface. And notice that the slope is 2 to 1, and that is where the specific surface gain a big effect. So now let's explore the data in more detail. We go back to the previous data set, and if they are straight lines in the log-log scale, that means that these are power equations. And so the permeability normalized by a reference value is equal to the void ratio by a reference value to an exponent b. And so we can say that the reference value is a void ratio 1, let's say. And so, by the way, this would vanish because this becomes 1. And so this is the permeability for any void ratio is related to the permeability at void ratio 1 times the void ratio at the power b. And now we have two questions. Question 1, what determines the permeability at void ratio 1? In other words, what determines the intersect of all these straight lines at void ratio 1? Let's take that permeability at void ratio 1 and try to identify what is the main parameter. By then, the void ratio vanishes because everything happens at void ratio 1. And if we do that and we plot versus the specific surface, indeed, the permeability at void ratio 1, at the reference void ratio, is a straight line with respect to the specific surface in log-log scale. And so you see this is a factor of -2, meaning that the specific surface will be inverse, will go to the denominator to the square, like we saw in the Kozeny-Carman equation. Indeed, the data is totally confirming the intuition gained from the physics, even though the Kozeny-Carman was done for all pores of equal diameter and parallel tubes. So now that we realize what determines the permeability at void ratio 1, which is totally controlled by the specific surface, now let's try to see what the exponent is. And it appears that the exponent increases with the specific surface. So on the right-hand side, you're going to see the clays. On the left-hand side, we have the sands. And the exponent may vary between, let's say, 3 and 4 or 5. But really, there are lots of outliers in this trend. So we cannot really have a categorical conclusion. But the exponent determines the relationship between permeability and void ratio. Let me go back and insist what this exponent is. This is the exponent b that we are looking at. We already saw that the permeability at void ratio 1 is a function of a specific surface. We are looking at this exponent b. And while there is some trend with increasing a specific surface, increasing the exponent, in other words, the sensitivity to void ratio changes, we cannot really conclude categorically. Nevertheless, this was the Kozeny-Carman equation. Now this is what K0 is. This is the -2 exponent that you saw before. And this is now the exponent B. When we replace those with what the empirical data tell us, we can predict that the permeability in units of centimeters per second is in the order of 10 to the -5 times the inverse of the specific surface in meters squared per gram squared times the void ratio with an exponent B, which is going to vary between 3 and 5, which needs to be confirmed for your soil. Now, when we do that for all the soils, and now we try to compare the predicted versus the measured permeabilities, we see that even though we have calibrated the model with experimental data, we still have an uncertainty of, could be 5 times larger, 5 times smaller, so 25 times. We have an uncertainty of 1.5 log scales. And this is what is puzzling, because even if you get a value, a center value, you may need 5 times more pumps than you think, or you have bought a pump which is 5 times larger than you anticipated. The uncertainty in permeability has a huge implications on engineering designs. Now, what other things affect permeability? Well, go back to the revised salt classification where we highlighted the importance of fines. Remember that there were 2 thresholds. One threshold where the fines were plugging the large holes between the coarse grains, and another threshold when there were enough fines to separate the grains. The second one was for mechanical processes, but the left one, this one here on the left, is where the hydraulic conductivity gets shut off, and it becomes, well, not shut off, but instead of being very large, in the case of clean sands, now it becomes controlled by the fines. And as you may remember, you need a relatively small percentage of fines to really produce a dramatic decrease in hydraulic conductivity of orders of magnitude, because it goes to the inverse of the specific surface squared. And this was the gravimetric relationship, volumetric gravimetric relationship that we determined to compute the fines content when this saturation of the pores takes place. The other thing is that even if you don't have enough fines to fill the pores, these fines are in most cases not load-bearing. And as the fluid flows, they can be displaced. And if fluid is converging to a well at the center, something interesting happens. They begin, because of inertial effects and lots of details in a paper with Valdez, but you will see that they begin knocking at pore throats and falling behind and eventually forming a clogging ring. It doesn't happen at the well. It happens at a given diameter where these inertial retardations begin to take place. But when that happens, the permeability will decrease dramatically. In the petroleum industry, they call this formation damage. Now, let's learn a few more things from pore network models, which we have done in other videos. You may want to refresh, but the essence is that the flow converging to a node is the sum of the flows that comes from all the interconnecting pipes. And then if we use the Hagen-Poiseuille's equation, now we can relate all these flows by the tube radius and compute the pressure at the center node as a function of the pressure in the neighboring nodes, weighted by these alpha factors, which come from the Hagen-Poiseuille equation. Eventually, this is a system of equations which you may solve iteratively. In the video before, we did it with Excel, with a solver in Excel, but this is basically a system of equations that you can invert to determine the pressure at every single internal node. Now that we have this ready, we can play with network models and one thing is that we may want to define the network with more interesting connectivities. It doesn't have to be just like a cubic pattern. It could be 2D with different coordination numbers, or it could actually be 3D, and the 3D could also be more complex. But if this is a mixture of tubes, these are tubes of two different diameters. There are large tubes, which are 5.62 times larger than the small radius. And the reason why we use that, because now that gives us a ratio to the fourth. The ratio of the radii to the fourth is 1,000. And so when we now look back at the predictions of what is the hydraulic conductivity of a mixture with respect to the hydraulic conductivity, if they were all large tubes, we see that as the fraction of small tubes increases, of course, the permeability decreases and it goes to the shut-off value, which is basically a percentage, the 1,000 ratio that we have here, because if all the tubes are 1,000 times smaller than all the tubes when they were all large, then the permeability will drop in the same amount. And you see how these major breaks occur at different ranges depending on the connectivity. So be careful when you do pore network simulations. You may want to get the right 2D, 3D geometry, the proper connectivity. Connectivity 4, like in simple cubic packing that we have described, is probably simplistic, even though it is very intuitive. Now there are two issues that we may want to explore. The pore tube diameters vary, the pores and the pore throws vary with a standard deviation related to the mean, which is in the order of 0.4, and they are log normal distributed, so we can explore the effect of pore size distribution, and we can also explore the fact that layering will tend to produce fine, coarse materials with long lateral correlation length, but with a very periodic structure in the vertical direction. So all this can be done. And to show you briefly some of the results when we play with this, here it is. We are looking at the fraction of different fractions of small tubes, and here it goes from 0 to 100. And we're asking the following question: how many tubes are responsible for 50% of the flow? If all the tubes are small, 50% of the tubes are responsible for 50% of the flow. If all the tubes are large, once again, 50% of the tubes will be responsible for 50% of the flow. Clearly notice that the flow, when all the tubes are large or all the tubes are small, are going to be completely different for the same pressure gradient. But here we're just wondering about, for a given flow rate, how many tubes are responsible for that flow rate. Interestingly enough, when you have a mixture of 50-50, 50% of the tubes are large, 50% of the tubes are small, a very small percentage of the tube, less than 10% of the tubes, carry more than 50% of the fluids. However, when more and more fine tubes are forming the matrix, then the large tubes become increasingly more isolated and they stop carrying flow. So this interplay in this geoplumbing, the interplay between large tubes and small tubes is quite intricate, and these are beautiful. Pore network models are beautiful to study this interplay. The second aspect that we were talking about is not only the variability, but also whether they are correlated or uncorrelated. Uncorrelated, they're all in random patterns. And you see that, yes, there are some tendencies of creating avenues. In this case, the line thickness are proportional to the flow rate in each of the tubes. So there is some tendency to channel even in totally random pattern. Now, if now we run a function that the kernel that creates a correlation length, so even though the pore size distribution in the upper simulation is the same as the pore size distribution in the lower simulation in each of the three columns, As you can see now, the fact that there is a spatial correlation, there is higher probability that large tubes are connected to large tubes, which are connected to large tubes. And so that now creates a very pronounced flow channeling, which is what happens, of course, when you have horizontal flow in a varved clay or in a layered stratigraphy. And eventually, a significantly smaller percentage of the tubes are responsible for most of the flow. Finally, there are some mathematical rules that you can use to estimate what is the upper bound or a lower bound when you have a mixture. For example, if you have a layered soil and you're flowing normal to the layer, then the least permeable layer will tend to be the one that slows the flow the most. And so the equivalent hydraulic conductivity is the inverse of the sum of the inverse of the permeabilities, which are prorated by their thickness. And this is because you are looking at the total pressure drop. Conversely, if flow is taking place parallel to layering, so imagine that this is actually reverse. It's very weird to have this type of a stratigraphy, but so rotated 90 degrees, if flow is happening parallel to layering, the more pervious layers are going to be the ones that are carrying most of the flow, but all the layers are subjected to the same pressure difference. So now you're adding flow rate for each of the layers, and so now the averaging is the arithmetic mean rather than the harmonic mean. Now there are other patterns and there are other closed form solutions. Let me highlight another one that is particularly valuable, which is the Hashing-Strickman. Hashing-Strickman give you also upper and lower bounds, which are narrower than the series and the parallel bounds. And so they tend to be preferred. And now we can use these bounds to go back to the problem of just a network of two sets of tubes, and you see how the Hashing-Strickman are going to anticipate the boundaries. This is when they are all parallel, when they are all in series. The Hashing-Strickman are just a little bit narrower in this case. But the fact is that because of the prevalent role of large pores, large interconnected pores on permeability, the uncertainty on permeability, hydraulic conductivity can be quite large. So we cannot automatically assume the various averages. Sometimes we have to consider the upper bounds and the lower bounds in our analysis. Let me invite you now, before you leave this video, to create your own summary. What are the take-home messages? What are the most important points that you would like to keep in mind? Of course, you have to start from the physics, and the physics tell us that drag controls hydraulic conductivity, and drag is proportional to specific surface. Therefore, hydraulic conductivity is going to be very sensitive to specific surface, and in fact is pretty much proportional to the inverse of the specific surface squared. Void ratio has these combinations or porosities in the numerator and the denominator. It does have an effect. As you saw, permeability follows a power law with void ratio, but altogether, the effect is not as pronounced as a specific surface. Specific surface is critical. And you may remember that the specific surface is controlled by the smallest particles. And therefore, if you go back to empirical equations that we use in the geotechnical literature, it is quite appropriate to say that the fraction of particles which pass 10% of the total mass, what we call the D10, is indeed a very good indicator of how low the hydraulic conductivity will be, because those particles are the ones that provide most of the specific surface where water is going to drag against as it flows through the soils.